Okay, thank you for inviting me. So indeed, I'm actually one word of warning. So I'm in the end a physicist by training, and what happened is 15 years ago I got pretty interested in my experiments. I was a postdoc at the time, and I got really interested in my experiment when it came and said we need to start over with our computing system, and and that's kind of how I started getting involved in software and computing work. Indeed, and as it turns out, so CMS is the experiment I started working on about 10 years ago, and at this point I'm running the software and computing project. There's two of me doing that, but it's about a project of quite a number of people, probably about 100 people contributing directly to our project, and it's a worldwide project which brings lots of challenges. So let me see how to go forward. Okay, so just an outline to kind of introduce the sorts of things I'll talk about. So I'll talk a bit about LHC and CMS specifically, just to introduce the sorts of challenges that we're facing and the physics we're trying to understand. And I'll talk a bit, and then I'll interleave the next two sections, which are to introduce how we're doing software and computing for our experiment now, and also what we're looking at for the future in terms of things we can change, because in the end our experiment is expected to run for about another 20 years. Okay, so this is a photograph of what our accelerator complex would look like if it was above ground. So it's a red line on a PowerPoint because it's about 100 meters below ground, but it's located in Geneva, Switzerland, so it's bordering the Switzerland and France in that region. So the tunnel looks something like this cartoon, which is about a 27 kilometer tunnel, 100 meters underground, with a series of superconducting magnets running through that provide the acceleration of our beams. So the experiment I'm working on is called CMS, which stands for compact muon solenoid, which I'll show a bit more about, but it's certainly not in any way compact, but it sits at one of four main experimental locations around the ring. So the facility is able to give all four experiments beam for its physics at the same time. This slide was just to give you some perspective on the size and scale of things. So I talked about the tunnel was some miles slipped in instead of kilometers. Sort of 30 kilometers. And it was a big project to build this tunnel, but that was about 30 years ago that happened. So what gets accelerated around the magnets are two beams made of protons, where they're essentially broken up into small bunches separated by 25 nanoseconds. So as I talked about, there's four main interaction points, where CMS experiment is located at one of those. And I think the accelerator actually is a pretty interesting achievement on its own. It's really the largest cryogenic system in the world, and it is essentially a field of research unto itself. Okay, so this is an enlarged picture of CMS, which is it's an artist drawing, but I think it's useful to show mainly because it shows that CMS is made up of different pieces, and actually it was lowered from the surface laboratory down underground in these large pieces. So basically this very large experiment, which is 14,000 tons, went down in about 20 pieces, which you can imagine took a long time and some really special equipment. But the main idea of CMS is that it's essentially a big camera made up of about 100 million channels of essentially 100 million pixels. You can think of it that way, where different from a normal camera. There's different technologies are designed to detect different types of fundamental particles that then get merged together into an overall picture. Okay, so this is a real picture of one of the slices, and you can see in the bottom of the screen people, just to give a perspective of the scale of this. It's really quite a massive experiment. So this is one of those slices you saw in the previous slide, and what happens underground is that we're able to move these detector slices together or apart for maintenance, but in a normal condition they're all squeezed together so that you you get this. The idea is you want to surround the point where there's particle interactions, which is with as much instrumentation as you can get. That's the underlying design. So it takes a lot of people to make CMS happen. This is a picture of our surface facility laboratory with probably a quarter or a fifth of our total collaboration, which is typically about how many people we can get together at one time. So it's really a massive undertaking of people, and of course I'll talk about the work of a lot of people other than myself. But that's, I think, one reason why this project is exciting is that there's really a large dynamic of people that we get to work with. Okay, I just had 2 slides, just try to talk about the scientific goals, where in very broad brush, it's to understand the fundamental interactions of particles, it turns out the best way to do that is to look at very high energies, where instead of studying the sorts of normal matter of protons or neutrons, that those pieces of matter break down into different constituents that we're able to study with a very high energy accelerator. So when CMS started, so-called standard model of particle physics looks something like the diagram on the left, which, if you ask the theorists, there's really one missing element, the so-called Higgs boson, which had been predicted long ago, but had not been experimentally observed. And I think that the point of the picture on the right is really that there's lots of reasons why physicists think the standard model is a really good theory. And I think it's regarded as, certainly in our field, it's regarded as the big achievement of the last half century. Okay, so you probably know that the LHC in 2012 announced the observation of the Higgs boson. So just some pictures of that. So this was a very big news event, and ended up resulting in the Nobel Prize essentially a year later. So the plot on the bottom right is really the final product of a huge analysis done by the experiment, where it's one of the final projects where in the end the Higgs signal is this small bump on this graph that really takes a lot of scientific experience to know how to interpret properly. But behind this is a large product of scientific and computing work. Okay, so the obvious question to answer is, well, I just completed the standard model, am I done? The short answer is no. There's lots of things, and the main reason for that is that the same theoretical community tells us that there's very likely more to find, that our standard model of physics is not complete or is not correct. It looks correct to us given the sort of experimental regime we've been able to query, but if we keep looking at higher energies, then there's more to see. So the idea behind now in the LHC is to look for those extra things that we haven't seen yet. So the LHC is, of course, not alone in that search, but it's really an excellent tool for all these searches. And so one example is that we know from astrophysics studies that there's a large amount of what's called dark matter in the universe, that sort of what you see in terms of gravitational pull and what you see in terms of visible stars are not consistent. And so the idea is that the LHC may be but on the other hand, you don't know what this dark matter is, and so the idea is LHC is may be capable of generating that dark matter and thus being able to isolate it in the laboratory. So the really big difference between an astrophysics experiment and LHC is that in LHC we have this essentially nice camera around the one point where you expect interesting things to happen, so that if something interesting happens, you will really get a nice picture of what it is. Okay, so I mentioned that LHC is a project expected to run about 20 more years. So we're all the way on the left at the green arrow, roughly, and there's lots going on in this graphic. I think the main point is the blue line, which is just a measure of how much data the experiment is expected to get over this time. So this goes all the way to 2038, so 23 years from now. And you can see on the absolute scale of things, we're just beginning to get the data that we're hoping to get over the lifetime of this facility. I think the other challenge is that let's see, can I see it? I guess it's just shown in writing. This is the trigger rate. I'll come back to what that really is, but it's a measure of how much data we're taking per second, and trying to save for analyzers to use, and that's has grown over the last few years, and will essentially pick up another factor of 10 between now and about 10 years from now. Okay, so now I have too much animation on this slide, so I better stay over here. So I wanted to start with a summary of experimental challenges and then start talking about the computing. So I think our biggest challenge is that we get 40 million beam crossings per second, and in each of those beam crossings gets roughly 20 or 30 collisions. So that's basically a billion collisions per second that we have to sort through. So the unfortunate thing from the science point of view is that most of those collisions are not the ones we're looking for. That we're often looking for 1 in 10 billion or 1 in 100 billion sorts of collisions, and so it's very much we say needle and haystack sort of problem, where you're really searching for something small in a large pile of data. Okay, so the next challenge is that we can't afford to keep all those events, writing them out to disk for people to look at. That for most of them we have to decide in essentially real time if we want to keep them or discard them. So we keep about 1,000 events per second, and that's what I mean by triggering. We say we trigger on an event, which means we decide we want to keep it for later. Okay. Right. Okay. So I'll skip through the animation. So right, this is what I talked about. There's basically 2 levels of trigger. One that happens in electronics very quickly, and another one that takes where we use a large farm of computers, and we take about 1/10 of a second to do that analysis. So once you get to this step, you have about 1,000 events per second to deal with, that you then save. You then save all of those to data to essentially disk, to be available for the collaboration to analyze quickly. So that's still the big challenge, which I'll show on this slide. Just to put those, so I talked about events per second, can translate that into bytes or bytes per second, but the units are really terabytes per second coming from the detector. That sort of first stage trigger, which happens in milliseconds or microseconds, is processing about, or the output of that is about 100 gigabytes per second. Typically is an FPGA-like technology, something able to make very, very fast decisions. So those tend to be custom crates of electronics. Then the second stage is, as I said, CPUs. There's essentially a big farm sitting next to our experiment. The output of that is about 1 gigabyte per second. So that's the sort of data stream that we end up analyzing in our offline computing facilities where I work. There's a bit of processing that happens, and then what the analysts actually end up using is about 50% of that, sort of 0.4 gigabytes per second. But of course, one analysis does not use the entire data set. They use a fraction, but you end up then having hundreds of analyses going on at any one time. So the pretty unique thing from the analysis point of view is that this is a very distributed system. This graphic is probably too small to really read, but I'll come back to it on the next slide. But it's a scale of computing that we don't tend to do in one location. We do it in a distributed computing network, which gives us more computing than we would have otherwise. So those are the numbers that we have today, which today we're in run 2 on this diagram. This is just a cartoon that shows the data rates and how they're going to grow through time. So run 4 is sort of 2026, and so you can see CMS is in the yellow, that our data rates will grow by a factor of sort of 20 or more on that time scale. And so there's while there's lots of interesting computing problems today, we have a big challenge coming in about 10 years for our experiment, and being able to calculate through all of that data. I think another theme that I'll come back to a few times in the talk is on the software. There's a natural pressure on when you're trying to do computing for science on such a scale that you want to be able to do it as cheaply, as efficiently as you can. So you're always asking, can I write faster software? And the graph is to show that this has 2 points really. The first is that so run current is to say run 2, and the other line is for run 1. So that's a span of about 3 years. And the point is that we've been able to reduce the resources we need to do our event reconstruction by about a factor of 3 in a few years. That's the first point. The second point is that as luminosity increases, so that's the x-axis of the graph, that the time to process an event grows exponentially. So that is to say that from an offline computing person's point of view, there's 2 challenges that then multiply. That the luminosity is growing, so that means events are more complex and that they're harder to process. And second, the trigger is keeping we trigger on more events, basically an order of magnitude more events in the future. And so there's 2, so from a how much computing power do you need point of view, you multiply those 2 factors together. And so there's another reason to conclude that in the future we have a truly massive problem to solve. Okay, but before the future, I'll talk about a bit what we're doing now. Okay, so I showed on a few slides back this distributed computing network. So that's the Worldwide LHC Computing Grid, or WLCG, which you may have heard about in other contexts. So the pins on the map show, at least in cartoon form, where the large sites of this grid are located. So the idea of a grid is that you have large computing centers that are connected together by good networks. So in total, there's about 250,000 CPUs running on any particular day. That number has grown. I think it's probably 350 at this point, but okay, once you get to that scale, things are pretty similar. The total storage is about 200 petabytes. And then I mentioned networks. There's sort of globally moving 15 gigabytes a second of data around the world, and that's I think really a big number that we've become to rely on. That if your site does not have good connectivity to essentially the rest of the scientific world, then it becomes a bigger challenge for us because we've gotten used to having this good connectivity, and I'll come back to that. What was too small to read on the previous graph was that this network is built up of sites that are some are big, some are small, and there's a hierarchical. It was built with a hierarchical system, when that there's the home institution. So CERN is called a tier 0. It's meant to be a unique, very large facility, and then there's about 10 what's called tier 1s, creatively, around the world, which are meant to be regional centers. Essentially, there's one per large country, and then a few others geographically located, and then those are the big sites, and then there's lots of smaller sites called tier 2s, which were designed to be close and work together closely with one of the tier 1s, and the idea was the tier 2s are where an analyst actually goes to do their computing. So that you have a new good idea for an analysis to do, and you go find which tier 2 is hosting your data, and then you can use that tier 2 for your processing. So that model has changed a bit, but that's the general idea. And okay, so I tried making a list of different technologies we're using, partly just to say these are interesting ones for someone wanting to collaborate with CMS, knowing C++, Python, and GitHub are interesting ones for us. We've started using sort of continuous integration technologies, so we've chosen to use Jenkins. Then Root is, I think, the other label on this graph. Root is a high energy physics specific data analysis toolkit. It's, if you know MATLAB or R, it's a kind of an equivalent to those, except it has a bit of a different view on the universe. But from sort of our software point of view, its main use is that we put all of it has very good compression and streaming functionality for complex data types. So we're able to take a C++ object and stream it into we call a root file, without having to write code at an object by object level. We're able to just say, I have this list of electrons. I want to save them for future analysis, and I just use root to do that. And it means that 99% of our analysts are completely ignorant of how that works. They just know it works. Okay, so going back a bit towards our processing model. So I talked about having 40 million bunch crossings per second, which really means we have about 1,000 bunch crossings per second that we have to analyze in the offline computing sense. The most important point for us is that those events are all independent, which is very different from if you're doing a plasma physics type of analysis where you get a whole big pile of data, but you have to analyze it all together. So for most of the processing we do, these what we call events are all independent, and we can process them independently. So this means that for the last 30, 40 years, high energy physics has done things in a really embarrassingly parallel method, where you can go from analyzing one event to analyzing 1,000 events just by using 1,000 CPUs. That you don't have to write any parallel software. You just run 1,000 applications at the same time. So what this has meant is that over time, the best, if you're a scientist, you want to optimize how many events you can process per dollar of computing that you buy, right? So the best way to do that is just from commodity computing, which is say your Linux desktop and this has been true basically my entire career, I think, which makes me quite lucky. People used to think about this much more, and it looks like that. I think one of the points of the talk is that in the future we're beginning to think that this won't last, that we'll have to start thinking about other technologies. And okay, so the famous reason why that's true is that Moore's law has basically let us keep up with our growing data samples while not asking for more money for our computers. So we're able to say every year I need so many dollars, or in CERN's case Swiss francs for computing, and that by getting more computing per dollar because of Moore's law, we've not had a problem. I think the other important point about our applications is that different from a lot of applications they're pretty memory hungry, so we tend to need 3 gigabytes per CPU core, which I think on the scale of things is relatively a lot, and it means that as computing technology moves towards having smaller memory per core, we're having to make adjustments for that reason. But of course, from our scientific point of view, our goal is to make sure that we can continue to use cheap computing, if you will, and to use it efficiently, because once we stop being able to do that, then our sort of the cost of doing an analysis goes way up, and we of course can ask funding agencies for more money, but they probably will say they might not say yes, let's say. Okay, so I had one slide here on our software framework. So you can imagine we have developed, given basically 2,000 people doing analysis, we've put together and support a framework for analyzers to work together, both in the sense of there's always 10 people doing one analysis together. We want to facilitate them working together, but also to facilitate, once you do an analysis, to be able to take the code that you wrote and reuse it later, or more importantly, have somebody else reuse what you did later. So it's particularly important, and the experiment thought a lot about this reconstruction framework before the experiment started. And the idea that people came up with was that, okay, because events are independent, we'll design our framework around the concept of an event. And then what happens is that an individual user writing an algorithm, that algorithm can take data from an event and add data to an event, basically independently from all other algorithms. So this basically allows users to plug in new algorithms as they want without having to worry about how their algorithm interacts with another algorithm. So this was just an example where the analyst has 3 different components, an input and an output. So in reality, we have not 3 components, not 3 different algorithms, but tend to be hundreds for some of our processing steps, which becomes quite complex, but in the end they're built up of basic building blocks. And this becomes a big benefit when we start thinking about parallel computing problems, that you can imagine this naturally parallelizes, because you have lots of different algorithms which are by design independent. Okay, the other software we write is essentially managing workflows, so you can keeping track of scheduling requests from so many users and on so many CPUs when all the requests are a little bit different is a big challenge. So the WOCG itself provides some tools to do that, but we have to talk to those tools, and of course the typical CMS analyst doesn't want to develop such tools, so CMS has developed or really continues to develop such tools, where the idea is it handles communication between a user doing an analysis and the computing infrastructure across sites, so that the details are known to a small set of people. And when you're writing your thesis, on the other hand, you don't have to go learn about all these things. You can use something that already works. Okay. So I talked about a distributed computing network, so that's kind of this side of the graph. And then this side of the graph are different algorithms that we run at large scale in production. So we do simulations, we reconstruct data, and we do analysis, are the three main things. When we started taking data, these tended to happen on specific spots. And what's happened during run 2, actually whoops. Oh yeah, that worked, okay. So what's happened during run 2 is that we've tried to basically make all of these sites look the same. So the idea is that your computing grid stops looking like a computing grid and starts looking like one big facility if you're a user. Of course, if you're a maintainer, it's a very different statement. But the idea is that if everything looks the same, it's simpler from a user point of view to use. Okay, so I mentioned networks in the introduction. This is a graphic that maybe explains better what I said, that there's a tier 0, a few tier 1s, and lots of tier 2s. And these, in our model, now it's very important that these sites all are nicely interconnected. And 20 years ago, when people started thinking about LHC computing, it used to be the tier 1 the tier 1 talked to tier 0, but did not talk to other tier 1s. And similarly, the tier 2 talked to a regional tier 1, but did not talk to other tier 1s, did not talk to other tier 2s. And you can see that's what's changed over time, is that networks, the scientific networks around the world, have gotten good enough that tier 2s can talk to each other, can talk to any tier 1, and similarly tier 1s can talk to other tier 1s as well. So this is a pretty interesting graph that the fonts are probably too small to see, but it's on a log scale, the transfers that CMS is doing per week over the last decade. There's various colors that are not too important, but the idea is over basically a decade, we've gone from 0 to, this is 2 petabytes per week of data transfers. And that's of course good in the sense that it says networks around the world are really made giant progress, and it's maybe scary in the sense that it really isn't a sign in how we rely on these networks. This graph is actually the same sort of information on over a longer time scale and showing a different way, but just showing that basically networking has grown linearly over time. But in terms of, so of course we're always thinking of how to take advantage of this better, where it comes together is how we manage data. So we have this we call data federation, which is to say trying to make our distributed sets of storage look like one coherent storage system, but it's really a storage system and not a content delivery network. So we're not yet thinking like Netflix or some other company that has large data that users want in real time, and no matter where the user is in the world, they're able to get to that data quickly. So that's one challenge: is can we make what we're doing look more like, look more transparent to our user community? And I think from a pure networking point of view, can we make network throughput predictable? We're always doing analysis or doing our production. We're always challenged because we don't know very well what to expect from a particular network link. That sometimes your throughput can be very high, and sometimes it's much lower. And it would be fine for us if we knew how to predict that, but instead, basically by experimenting. So if these things were predictable, we'd be able to do much better job of deciding, well, my data is at site X, and how do I make best use of that site Do I transfer the data or not? Because, for example, the CPUs and the data are not necessarily at the same location. Okay, so I talked about the trigger farm that we have. So one point of the LHC facility, like I think most other certainly accelerator facilities, that it's not operating it's not delivering the data to the experiment 24/7. So what that means is that we have this large farm of computers that is really busy when we're taking data and essentially completely idle when we're not taking data. And so one of our recent research points has been into how can we use this facility when it's not taking data. And the graph on the left just shows the sort of typical sort of duty cycle our experiment sees, that the red and blue lines say we're taking data, and then which means the points where we're not, which are the yellowed out graphics on this screen. Those are where we have opportunities to use the facility for a computing system. So it's sort of 20 or 30% of the time these systems are completely idle. So the biggest challenges here is that you have this 10,000 CPU resource that suddenly appears and suddenly disappears with very little notice. And the challenges we've solved have been to basically be able to instantiate a large set of virtual machines quickly, and then to be able to shut them down quickly without causing problems to our computing system. And this was, the picture on the right just shows the sort of proof of concept that there's two types. This is a graphic of transfers, and there's two types of transfers. The ones above the line, above 0, if you can see 0, are when the experiment is taking data, it's always sending that data to our central computing facility for archiving. And you can see then there's always blips up and then blips down when we're not taking data. And then on the below 0 instead is an illustration of when we're using this facility for our offline computing needs. And the point is that the sort of startup and stop times are quite minimal. So it's been a big success. So how can we make this better? One way, and really the challenge remaining, is that if you're running a large computing facility, you like to run long jobs that are stable and they just run for a day and you don't have to worry about them. But here we end up needing to run basically 2-hour jobs. So the challenges are around how can we improve our resource scheduling efficiency for such short jobs. One way would be to run longer jobs but checkpoint them. And we don't know how to do that. At least we don't know how to do that on such a large scale. So basically asking 10,000 processes, stop, save your state, such that I can get it back later, but do that very quickly in a few minutes. The other way to improve our efficiency was if we could do basically event level bookkeeping. So that's to say to know how to keep track of where 1,000 events per second worth over a few years, where all those events are at one time. So what we do now instead is we track data in basically 20-second chunks, so that we know we have or don't have a chunk of 20 seconds. So it's making things really 10,000 times more complex than they are now. But I think that's one of the sort of research questions that if we had a solution for would make our use of the system much more efficient. Okay, so another area of complexity is managing requests. I tried to write down kind of our workflow of, if you're a user, you want some simulation. So from the user would like to go from the first blue box to the last blue box without worrying about anything in between. But in between, we're doing lots of consistency checks, checking the resource usage, making sure the user's request is valid, essentially. And once all that's done, we can start the production. But of course, the work is not done at that point. Even though we are working hard to make our system look like one big computing site, it's not one big computing site. So you have to ask, where can I run the jobs? And then, of course, jobs don't always work. So you have to monitor their progress and make sure that the user can monitor their progress. So this, of course, is a process that in the end we're making sort of on average, I think a few thousand requests like this per week. And there's, of course, on bulk, things work really well because things are managed through a set of database-driven tools. And so when things are working, everything's great. But there's always, I think from our point of view, there's a few challenges left. First, there's always a problem somewhere, and you'd like to be able to more quickly detect when there's problems, and maybe even better than detect, to be able to fix. And then second, there's always a question of how can we use new expertise to understand how these various tools can be done more efficiently. I think it's a problem that's much bigger in hydrogen physics. It's much bigger than problems we've had in the past, but I think it's not maybe not a huge problem on the scale of companies. Okay, so I talked in many places about having a large computing facility. So the consequence of having a large scientific computing facility is that you're always asked, are you making good use of your resources? Which is to say, are your CPUs doing something? I think once we are always able to answer that question, the next question is, are we using our CPUs for something useful? But right now, the hard enough question is, are we keeping our CPUs busy? Which is to say, what we would love to have is a set of requests from our science community that were always constant in time, that we could just keep our processing and our disk and our tape always working at the same level. But life is, that's not really the way science works. That science works more like this, that there's a conference coming up and you'd like to be able to meet the demands of that conference, which is to say that you have bursts of in particular processing. So one way to solve this is if we owned fewer resources and used commercial cloud providers to fill in sort of burst activity, so that essentially we provision, which is to say we buy resources for the constant level of processing, and then when you need extra computers for a month, that you essentially buy the computer for the month, not for its lifetime, by using a cloud resource. But of course, taking advantage of cloud resources really implies that we've done a good job with our data federation, and that the CPU and the storage don't need to be at the same spot, and that your network is good enough to allow that to happen. So I think over the last few years we've started experimenting with this. So in CMS we have a large project with Amazon Web Services. We're trying to essentially use Amazon to provide us the equivalent of our tier 2 facilities for a month, which is really the model that we would have in mind, that you need a month of CPU because of a conference or some other deadline, and that Amazon, you would pay Amazon to provide that for you, instead of having to buy all those computers all the time. CERN is CERN and the EU in general are looking to buy some fraction of the resources to do an experiment buying some fraction of the resources from cloud providers, and they're of course in the process of asking experiments how this would work. But over the next year or two, that the CMS will will learn how to use these systems, and so it's a nice, interesting research opportunity if to learn how to use clouds for science, essentially. But there's, I think, a big opportunity if we manage to do it, because it's a good way. There's always pressure to use resources more efficiently, and that would be a big step. But on the other hand, I should have talked about the last point. I think the new thing for us would be that in resource scheduling, is you have to decide when to use resources that you don't own. So resources that cost money, you have to do some sort of optimization to decide, based on my experience, is it worth using these extra resources or not, or should I just wait an extra day and use my own resources? Okay, so this slide actually changes gears. Talk more about, well, it's really a combination of software and architectures. So I introduced the concept of that we really historically have relied on embarrassingly parallel on computing systems, and in particular software, which meant that we've been able to write code that's not thread safe at all, and we've been able to scale that up to 100,000 CPUs just by running 100,000 copies. But what happened, this graph is getting old actually, but what happened 10 years ago is that this concept of Moore's law in the sense of clock frequency has stopped growing, which it had over a long time, which is to say that CPUs became multi-core and they're becoming many-core. So that this is slowly pushing us away from this concept of embarrassingly parallel. I think that the more important trends are more in low power or mobile processes, and then I think joint with that are that you'll no longer have the luxury of using gigabytes per core of memory, or at least you can't do it efficiently. That there's bigger and bigger penalties for cache misses and anytime you're accessing the slower memory caches, that's effectively a CPU penalty. Okay, so what has CMS in particular done about this? Our first step was to take the framework I showed at the beginning and turn that into a multi-threaded framework. And I introduced why that wasn't so hard, which is that the users, instead of writing a monolithic application, users write small plugins that are essentially independent and are talking to each other in a well-defined way. So this graph is pretty complicated, but it's meant to say you end up doing threading by thread 1, thread 2, and down to thread n, and essentially the framework just has to know, is this module thread safe, yes or no, and is this module independent of other modules, and then it can basically schedule things in a CPU efficient way. So we're really up at this stage, which is just to say we're still running events. We're still running basically single events, but in a way that's done within a single process instead of individual processes, and that's saved us a huge amount of memory, which I'll show on the next slide. Of course, where we're going, which we'll get to essentially in a year or so, is that we'll be able to run parts of events on different threads, which should bring, the real point of that is that we'll be able to do, the scheduling gets easier, the framework has more flexibility in scheduling so that you can go from, you're not bitten by Amdahl's law, you can scale up to higher number of threads and still use your CPUs efficiently. So the next slide just shows kind of where we are now. So we've been using this framework for about a year. It's really blurry from here, sorry. Where this actually shows the memory reduction as a function number of threads that you're using. And so we're getting basically a 70% memory reduction from this, which has been really important. What I'm not showing is the CPU utilization. That is actually, we're really close to having 100%, well, let's say we're really close to having no loss of the CPU efficiency from the threading up to about 4 cores, and hopefully for next year's software that'll be 8. So, but on the other hand, if you're talking about mobile systems, or using low power Atom or ARM CPUs, you'd like to be up much higher if you want to be able to use those efficiently. And then the development challenges we have is that, of course, this requires some change to every algorithm a user has written over the past years, so we have to update those. We've done all the important ones, but and I think conjoint with that is, as a community, the physicists don't know how to program, don't know how to write software that's thread safe, let's say. And so we have to teach them how to do that, and it's even though maybe we don't have the expertise ourselves. So I talked a bit about low power. So the other place we're starting to look at are with, oops, I should have said on the bottom left, GPUs. So graphics processors and coprocessors like the Intel mixed systems. So this is probably too small to read, but we have through CERN a lot of experimental clusters where we're able to run CMSSW using the framework I talked about, and these are just some toy examples showing how that we're looking at things like throughput per chip or throughput per power consumption, so the number of events we get per watt, things like that on systems. And so moving away from the idea that we just want to maximize the number of events per CPU is starting to be not the right metric that we're looking in this area. And there's this is a spot where we've had a lot of collaboration with companies, and it's there's really an endless amount of work that we can do here. Okay, let's see. So something I know less about, so I'll say less about it, is on disk. Actually, it's unfortunate that I know less about it because disk is basically 70% of the cost of our computing facility is disk. So we're doing lots of work into how can we reduce the needed disk, and also trying to understand how we think disk will evolve in the future. I'll talk about the first of those, which is this concept of dynamic data management. So what we had done, and what our field has always done, is that a human, so the physics coordinator, makes a decision about what data should be available to users where, given a total set of resources. What we've done is replace that human by a computer, where basically we have an automated system that says, I have this much disk available, and in the past few weeks, people have requested these samples with such a frequency, and it just says, okay, this data sample is really popular, so I'm going to make a copy of it so that it's available to users more quickly. Because of course what you want to do is, users are asking for data sets, and you want to minimize how long they have to wait for them. That's the goal of the system. What we're looking at are things like how can we make this better? So you can imagine making a much more sophisticated metric. So using data analytics to be a bit more predictive than we are. We're essentially making adjustments every few days based on what we've seen lately, and then generally how to improve metrics. But then the other important point is this says nothing about deciding how much disk you need. Really, it's to actually make an impact on users' lives. We've made an estimate of that, but it's sort of outside of the system. As you can imagine, there's lots of research you could do into judging how many replicas, or generically how much disk cache do you need for your system. Okay, so yes, so one slide on a few other areas of research. One thing we've tried to do and haven't been successful is try to develop a computing system simulation. So our computing system being built of all these sites and potentially having cloud resources, you can imagine developing an agent-based simulation or other approach to try to optimize how you're using resources. I think something happened to this slide, sorry. Trying to either optimize how much your total throughput given your resources, or optimizing how you would like to distribute resources in the future given some constraints. We're working hard on generically automating workflows, and I'll show an example of that on the next slide. And then on the code side, we're always looking to modernize code. From the root community, we do have some links to C++ sort of gurus out there, and we're from them learning a lot about how to write static analysis tools for our code, how to make our code faster, how can we profile our code essentially, and then we're trying to stay on top of compilers so that we can use modern C++ features. It's good to take the first book I bought on C++. I'm glad that I got rid of at some point because it's truly obsolete. Okay, so this was one example of some automation we've done. So I mentioned we use Jenkins and GitHub at the beginning of the talk. We've kind of merged these such that you can build this system. So we have software releases, like everybody has software releases, and these include twice daily release builds, just to do sort of integration tests. They include whenever someone makes a request for new software, we run a set of tests on that, and then of course when we want to build a production release, we have those sorts of releases. And this process is now really automated. So now from my phone, I can open a GitHub issue to say build my newest release, and then I have to do a few steps of confirmation, but otherwise the system is basically talking between our integration system based on Jenkins and GitHub, and all that work happens for me. And these are, I think there's more and more of these sorts of things where we could learn from the computer science community on how to automate our workflows that currently take human time instead. Okay, so changing topics again. I think data analytics has become an important thing for us. We're probably behind the times here, but we're thinking about a number of different ways we could use analytics. Of course, we can use this for physics analysis. We've used, I think when I was a student, our field started using neural networks. We've graduated to more sophisticated machine learning techniques, but there's a lot we can learn. I'll show an example on the next slide. But there's lots of places where we could, we're basically doing monitoring based on static information and not trying to do real-time updating, whereas we know other people are doing it. It can be on our workflow scheduling, our resource scheduling, and I think the most interesting one may be on, can we learn how to do this in real time triggering, such that we can reduce that large trigger CPU facility that I talked about. So this was an example of our typical data analysis workflow. So the part on the left is basically the central computing system, and then the part here is what users take care of. So we have this concept of an n tuple, which is basically a large can be thought of as a large vector of information that ends up taking weeks of processing to actually make. And of course you need that. Our current way of doing analysis is you spend a lot of time making this quote-unquote n tuple, and then from that you can make the plots that discover the Higgs. So the question we're beginning to ask, but don't have the answer to yet, is are there big data techniques based on Hadoop, for example, where that could make this processing step much faster? That's definitely an area of interest for R&D that we have these days. Okay, so actually that was my last my last thing. Okay, but then the conclusion is generic, which is just say from our point of view, the software computing, you might think after 5 years of operating experiment that the software computing has reached a boring stage. This was really to send the message that there's that it's not in that state, and it's for one simple reason, that the facility is expecting to run 20 years. And there's no way that today's computing technology is going to look similar to what we'll have in 20 years. And so we have the job to try to stay on top of that technology and to modernize our system to be ready for that technology, and at the same time delivering good science output for given the technology we have today. So there's a nice mix between operating a system you have and figuring out how to improve it. And for us, it's a big opportunity to learn about new technologies through collaborations and develop tools based on those for our users. Great, thank you. Yes. So I didn't talk about that. So indeed, there's this CMS at home does exist. It's I don't know if it's official, if there's an official experimental status of CMS at home, but it's something where it's not completely done, let's say, but we have some set of users, and the challenge for us is that I talked a lot about our jobs wanting to run days for a day with 2 gigabytes of memory. That's a really bad model for a user's PC, where the user will often. That's another case where having jobs that don't run for very long and don't transfer very much data at one time is particularly good. And actually, that's the biggest limitation we've found so far, is that they like small. 100 gigabytes is 100 megabytes is kind of the chunk of data that CMS at home would like to have at any one time, whereas the rest of our systems want 10 gigabytes at a time. So there's a mismatch that we're learning how to address before making that a production system, because we of course don't want to waste. We don't want to advertise CMS at home and have lots of people using it and then not use the data because of a technical limitation on our side. So we're doing it. But yeah, there's a few people working on CMS at home that is, and there's a broader, I should say, beyond just CMS. The CERN has put together a team to help the experiments do CMS at home or Atlas at home kind of projects. So, because indeed that's a potentially large resource if you can figure out how to use it for us.
What do you do in order to keep changing or improving your system, and at the same time you have to provide a stable system for users to use?
It's a very good question. So on the software side, it's easier because we just have a software release that we try to keep stable for a year at a time. So our data operations is always every year there's a break at the end of the year, and so we take advantage of that break. Although actually, if you're writing your thesis, at least in the US, your thesis can take 3 or 4 years, and so if we keep old software releases around so that the student can write their thesis. On the computing side, it's a bigger challenge. Although that's really the idea of having a set of expert run tools, is that as long as you don't change the interface, that you can change the tool, you can change the details of the tool without the user noticing, let's say. We took advantage, we had a exceptional 2-year time, 2013, 2014, where we didn't have any data at all, and we used that as a opportunity to change the interface of some tools, and we'll have another one of those opportunities in a few years and we'll, I'm sure, take advantage again to make bigger changes. But right now, there's definitely you learn quickly, especially in the job I have, that making interface changes to that users see when you have so many users is not is a hard thing to do. You get lots of complaints, let's say, so we try not to do it.
Some large companies that use a lot of computers now, like Facebook, Google,
Yeah.
and now turning to building their own machines. Is considering doing that as well?
Really building your own machines? No, we have not. We have not thought of that. In some sense, I feel like we're going in the other direction, that we'll give our computers to Google instead, because they're, 5 years ago when Amazon Web Services started to really be a big thing, it was we judged it to be very expensive, and now it's become cheaper and cheaper, such that it's really competing. It really competes with the cost of CERN buying a computer, even though CERN doesn't want to make a profit from that computer. It just wants to it just wants to give them to us. That Amazon, because Amazon's scale of computing is now so big that, and Google, I think, is the same way, that maybe in a few years we'll be able to give them more and more of our computers instead of building them ourselves. I guess the one exception to that is I didn't talk about too much, that the first part of our trigger is basically custom, they're FPGAs, electronics with FPGAs, so those are all basically custom built historically. Although even there we're learning how to do less and less custom building there even. I think if we can use somebody else's technology, that's better for us. So. It's also better for the students that work on it, because then they can go get a job somewhere else using, if you're using technology that other people know, that's other people use, it's really benefit to the students, because of course as in any field, I suspect the large fraction of students go do something else when they're done. So it's important to make sure they have opportunities to acquire the skills they need to also succeed no matter what they want to do. So a few year positions that typically are filled by students or people just finishing their degrees that want some experience. Okay, so I'll start with the summer student program. So the link is for quote-unquote non-member states, which include basically any country not contributing to the treaty for CERN, is called a non-member state. So Thailand and the United States are both non-member states. So there's an equivalent program for member state countries, but this is the one for us. So the deadline is in January, and it's typically a 10-week program where there's typically you have optional, as I understand, optional lectures in the morning and tours of CERN facilities, and I think Parut will talk much more about this part. From the experiment point of view, so mentors like me select students based on their application, which I think the application is mostly just a curriculum vita saying, here's my education and experience. I think it's definitely helpful to mention if you're particularly interested in an experiment. That's good to mention. It's also good to talk about what sort of technology you'd like to use, and I didn't write it, but certainly making if you have some experience in technical areas, it's good to say what those are, because CMS is never has enough. I would call them technically oriented, but call them computer science type applications. And it's good, especially if you know Python or C++. Those are are good things to talk about on your application. Okay, and let's see. Okay, and so this one tends to be for the the mentors tend to be people on the experiments, or tend to be someone on the root project I mentioned before, or there's a few other sort of scientific software projects at CERN that tend to be mentors of this program. I think the majority of people applying are physics background, but I think, as I say on the end, we're always looking for a few more computer science type people. Okay, so the other program for students, which is definitely focused on computer science, is the so-called Open Lab summer student program, where Open Lab is it's really interesting concept that CERN has put together, essentially a collaboration between CERN, a set of companies, and then the CERN experiments. And these are the companies currently involved, and so these, especially the ones on the partners level, are contributing. They even fund positions at CERN and have their own people at CERN working basically on next generation. The typical case is that they have a next generation product that they would like to get some experience using, and the CERN use case tends to be an interesting case. So I talked in the previous talk about architecture, sort of next generation computing architecture tests done in collaboration. This is one mechanism, so collaborating with Intel specifically on that sort of thing. There's also other companies. So Yandex is a company doing kind of like Google, but in Russia apparently, doing lots of machine learning. It's another example. So this is really a pretty interesting program, and it has a similar deadline in February. So the problem with this program is that last year it basically has an exponential growth in number of people applying, and if I understood right, last year about 3% of applications were accepted. So it's certainly not the only student program you should apply to in a year, because even if you have an excellent application, your chances are not so good. But it's a very good program. I think one nice thing is you can look at all the previous, at last year's lectures, which have all been videotaped at that other link, which is, I think, probably a valuable resource for learning about CERN in any case. Okay, so then the other category are not summer student jobs, but are really jobs. We have about 15 between the software computing, and there's another acronym which I won't explain, but it's part of what Pat is working on, is called PPD. Between us, we're really running a lot of the operations of the experiments infrastructure. We have about 15 people, 15 positions in our operations team that we have funding, and basically every 2 years we're replacing each of those positions. So the jobs are really they're not research jobs; they're operations jobs, which is to say managing all the transfers between our sites, or managing how our workflows run across our computing grid. But that's not to say they're boring. I think a lot of it tends to be how writing scripts or developing tools to make your life easier. They can be, I think, especially for the right people, these are very interesting jobs. So the positions, to explain more about the position, so they're open only to people affiliated with CMS institutes. So this institute is certainly one of those. So it could be anyone at that institute. You don't have to be a CMS or a CERN collaborator ahead of time. So a typical background of candidates that we're getting is a university degree or at most a master's degree, tends to be in computer science or computer engineering and then a typical application says that you know lots of programming languages. I think from our point of view, Python is the most important one. So truly knowing, which just happens to be the language we chose to use, is nothing particularly special about Python. And so we just went through and hired 5, I guess 6 even, new operators in the computing area. So it was the one useful point from me is that I got to see really a lot of applications, and it was surprising the number of people applying who had done something, even if it was just a month or two of getting experience either with CMS at their local tier 2 or other nearby sites, or with CMS technologies, so understanding a bit about grid, what the WLCG grid is, or things like that. Okay, so the positions are at CERN full-time. Typically, they last for us 2.5 years. There's nothing that says they can't be longer, but our idea is these are supposed to be sort of career-building positions, not career-making. You're not supposed to make a career out of these. Typically what people do is they come for 2 or 2.5 years and either often go back to school to get a master's degree or are hired somewhere else, and lots of people are hired by CMS actually, so that's in more permanent research jobs. So it's a nice opportunity. So these are because these are open only to CMS institutes, they're not advertised in the usual ways. They're basically advertised by your institution contact, who actually I forgot to look up who that was. It's probably, okay, Pat knows, yeah, okay. And that's it, okay. But anyway, these are both, I think, pretty interesting, and if there's another set of positions for member states that I didn't include, but I think for Thailand, these are the 2 opportunities that CMS has. And so then Open Lab, on the other hand, is run by, so Open Lab is a division of the CERN IT department, which is different from many IT departments. It's really the CERN Computer Science Research Group. And Open Lab is maybe the most focused on research of all the CERN IT. And then what's unique about Open Lab is that its main purpose is to develop relationships with these companies. And so I believe as a student, you would end up working with someone, the mentors for that program are all Open Lab associated people, and so you'd end up with basically collaborating for the summer between CERN and one of the companies on one of the specific projects that's already been established. So it's different, and then the lectures are different between the 2. I think just one is more focused on the non-member state program tends to be more physics lectures, and the Open Lab one is more computer science lectures. I think Brut will tell you he went to some Open Lab lectures as well last summer, even though he was in the non-member state program. What else can I say about it? Okay, and I think the other big difference is the level of competition is quite different, but.
Yes, but we used to have an agreement with CERN when we collaborate with summer students. So if one of the Thai summer students wants to go to the Open Lab, we can pay for them. We normally pay one student.
Okay.
Because normally Open Lab is by CERN. We pay by ourselves possible in future. But even a normal summer student can attend the Open Lab lecture open for them.
Right. Until they fill the room, I guess. Until they fill the meeting room, but.
Yeah.
But that's okay. Not a problem. Ah, that's good. I didn't know that. So okay.
But we know